Peace be upon you. Now, in part 41, we take the next step, and it sounds like pure mathematics, but it's really a story about why reality keeps coughing up whole numbers. Why do we keep finding integers in nature? Why does the world again and again insist on 1, 2, 3 instead of anything at all? Why do energies show up in steps? Why do phases lock? Why do charges come in packages? Why do quantum numbers refuse to be fractions unless some deeper topological permission is granted? The claim of this part is simple. When phi becomes representable, closure is inevitable, and the minimal non-trivial closure is a circle, S1. And once closure exists, integers are forced, not because someone wrote a rule, but because the geometry of returning exactly to the start creates counts. Closure forces whole numbers. And this is not a poetic preference. It's the strict consequence of our earlier firewalls. Part 39 demanded parsimony. Add no unnecessary structure. Part 40 demanded no units, no smuggled scale. Part 6 demanded gauge clean meaning. Only invariants survive. Part 37 demanded public comparators. Knowledge must be reconstructible. When you put those constraints together, S1 is not a decorative choice. It is the simplest place where go around and return exactly even makes sense, without importing infinities or special edges. Before we go deep, I'll add the brief note you asked for. The formal mathematical work behind these ideas can be found on Zenodo by searching Holophase. Imagine you wake up in a world with no landmarks. No mountains, no trees, no sun, no stars, no horizon. Just a smooth, featureless plain. You walk forward. Nothing changes. You can keep walking forever. Every step feels like the last step. It's not that you are trapped. It's that the world gives you no global clue. Locally, every small patch of ground is the same. Now imagine another world. You wake up again, and once again it looks like a featureless plain. You walk forward. You keep walking. The ground still looks the same at every step. You could easily believe this world is also infinite. But after a long time, something shocking happens. You return to your starting point. Not approximately, not close enough. Exactly. The same point. The same place you began, as if the world itself tied a knot in your path. Only then do you realize you were not on an infinite plane. You were on something compact, like the surface of a sphere, or a looped world, or any shape where far enough wraps back into here. Here is the crucial lesson. Locally, a circle and a line can look identical. A tiny patch of a circle looks like a straight segment if you zoom in enough. So if you only ever look locally, you can confuse infinite line with closed loop. But globally, there are different kinds of reality. A line is open-ended. No matter how far you go, you may never return. A circle closes. Far enough is home. Now take this lesson and bring it back to our foundation. Phi is the permission for distinction. In parts 3 to 31, we treated it as a silent enabling layer. In part 32, we installed windows. In part 33, we demanded coherence thresholds. In part 37, we demanded public comparators. In part 38, we demanded extensionality. If outputs match everywhere, theories match scientifically. In part 39, we demanded minimal structure only. In part 40, we demanded scale-free foundations. So now we ask, when we finally become able to represent phi, not to capture it, but to model its permissible structure, what is the least structure that can support consistent return? Because consistent return is not decoration. It is the heart of comparability. If I compare A to B and B to C and C back to A, I need to be able to say, did I come back to the same relation? Did I return to the same equivalence class? Did I close the loop of meaning? If return is only approximate, then sameness becomes vague. If return is impossible, then global consistency is never guaranteed. Comparability becomes a local illusion and collapses as a public structure. So we need closure. But parsimony says, do not build a palace if a hut will do. If the job is closure with no scale, we choose the smallest structure that provides it. What is the simplest closure? Not a sphere. That is already two-dimensional and adds extra degrees we have not earned. Not a torus. That adds multiple independent cycles, extra structure again. Not exotic spaces full of twists and identifications. We have no license to add them yet. The simplest, non-trivial compact manifold is a circle. That is S1. One dimension, no boundary, no edges, no privileged endpoints, no special corners. A place where you can keep moving and inevitably return. Now we make the leap from story to inevitability. If you want closure without smuggling infinities, you land on compactness. If you want compactness with the least complexity, you land on S1. And the moment you land on S1, something happens that seems like magic until you see it. A continuous loop produces discrete integers. Because on a circle, you can count how many times you go around. Once around, 1. Twice around, 2. Backward once, -1. This count is not a matter of units. It's not meters. It's not seconds. It is pure, scale-free counting of closure. Topology calls this a winding number. But you don't need the fancy name. You already understand it. You understand it because you have used the clock. Picture a clock hand. The hand moves smoothly, continuous motion, no jumps, no steps. It glides. But the clock face is a loop. 12 hours return to 1. A day returns. A year returns. Now imagine a broken clock universe, where the hand never returns. It goes 1, 2, 3, 12, 13, 14, 15, endlessly, like an infinite ruler rather than a loop. Locally, the difference is invisible. Between 3 and 4, both clocks behave the same. Even between 11 and 12, still the same. The difference appears only when you demand global closure. Does 12 go back to 1? If it does, you have a loop. If it doesn't, you have an open line. Now notice the deep point. If your world needs consistent return, if identity must be globally stable, then a broken clock structure is dangerous. It allows infinite drift. You can never certify you're truly back to the same phase because there is no back, there is only more. S1 closes that drift. It prevents the silent ground from leaking infinite, untestable structure into the public world. That is why we call it closure without smuggling infinities. Now we connect to quantization. On a circle, if something must return exactly to what it was, its value, its phase, its state, then the path around the circle cannot be arbitrary. The return condition forces a constraint. That constraint is typically, you must fit an integer number of cycles. A child can feel this with a simple toy. Tie a rope into a loop. Pluck it like a string instrument. What patterns can persist? Only those where the wave fits perfectly into the loop. One whole wavelength, two whole wavelengths, three, not 1.5. Because 1.5 doesn't match at the join. It tears itself apart. The loop forces an integer. That is quantization in its most naked form. A closure condition on a continuous medium produces discrete allowed states. Now scale-free, unit-free, parsimony-respecting closure gives you a universal origin of integers. You don't need a meter. You don't need a second. You don't even need physical space. You need only a loop condition somewhere. In physical space, in configuration space, in phase space, in field space, in parameter space. The loop can be visible or hidden. But if you find integers, you should suspect the closure invariant is whispering behind the scenes. This is why the core prediction of part 41 is quantization will always trace back to closure invariants, winding numbers, holonomies, or their equivalents. Not as a loose metaphor, as a structural law of what becomes publicly representable. Now, let's make this vivid with a simple journey. Imagine a road up a mountain. There are two ways to climb. One way is to go straight up the cliff. It is brutal, it is unstable. One slip and you fall. The other way is to spiral around the mountain. Each loop takes you higher. It is gentle and stable. It is how roads are often built in real mountains. Now look at what the spiral road does. It turns height, a continuous variable, into loop count. I am on my third loop is a discrete statement. Of course, you can still be halfway through loop 3, but the global structure divides your progress into countable wraps. The mountain does not need a ruler for this. It doesn't need meters. It needs only the fact of looping. In the same way, phi's representability introduces a looping structure that makes certain features countable. That countability is what later becomes quantum number. Now, if you want to see this not as philosophy, but as a repeating pattern across physics, we can scan the history of quantization and ask one question each time. Where is the loop? Start with the old Bohr model. In the crude early picture, an electron orbits the nucleus. An orbit is a loop. Bohr's quantization appears as an integer condition on angular momentum. Whether the old picture is literally correct is not the point. The point is, the integer arises when you demand that the orbiting wave fits in a closed path. Where is the loop? In the orbit. Now go deeper. Schrödinger. Schrödinger replaces orbiting particles with wave functions. The wave function must be single-valued and consistent. If you go around the closed loop in the relevant space and return, the wave function must match itself. Often, it may match up to a phase, but that phase must be consistent, and consistency yields integer multiples of 2 pi. Where is the loop? In phase closure. Go around and return. The phase must wrap an integer number of times. Now consider the particle in a box. Even here the integer appears. Why? Because the wave must satisfy boundary conditions. The wave must match required values at the boundaries. That's a kind of closure. Standing waves form when the pattern closes on itself between constraints. Where is the loop? In the requirement that the wave fits the domain exactly. Closure by boundaries. Now the Aronoff-Bohm effect. This is one of the clearest examples because it screams topology. A charged particle moves around the region where the magnetic field may be confined. Even when the particle travels where the field is zero, the phase shift depends on the integral around the closed loop. The observable depends on winding around something, not on local force. Where is the loop? In the path encircling the region. The phase depends on loop integral. Now Berry phase. change parameters slowly, and bring them back to the start. The system returns to the same physical configuration, yet accumulates a phase that depends on the loop in parameter space. Where is the loop? In parameter space. A cyclic change yields a phase holonomy. Now quantum Hall effect and topological materials. Quantized conductance is measured as an integer or rational multiple of a basic unit. The integer is a topological invariant, often a Chern number, linked to global properties over closed manifolds in momentum or parameter space. The key thing is, you cannot tune it continuously. It jumps only when topology changes. Where is the loop? In the closed surfaces loops of the relevant abstract space. Quantization is a global invariant. Now, the point of listing these is not to drown listeners in names. The point is to show the repeating fingerprint. Whenever physics produces an integer that refuses to smear into a continuum, closure is nearby. Sometimes the closure is literally a loop in space. Sometimes it is a loop in the space of possibilities. But topology keeps returning because topology is the mathematics of return, and S1 is the simplest return. At this moment, a skeptical listener might say, okay, fine, but why is S1 inevitable specifically? Why not just keep everything on an infinite line and still have comparability? Why do we need compactness at all? Why not allow infinite drift and still do science? This is a fair challenge, and our answer must remain firewalled. The answer is, we do not claim the universe cannot be non-compact in some aspects. We claim something more precise. When phi becomes representable as a value space for comparability, the minimal non-trivial way to support exact return without edges and without imported scale is S1. And the reason we care about exact return is not metaphysical, it is operational. Public comparators require that if we run a procedure that cycles through a set of states and returns to start, we can certify it returned. That's what a clock is. That's what calibration is. That's what repeatability is. And repeatability is the beating heart of science. A clock is not time. A clock is a cyclic comparator. And in part 40, we saw that units reduce to cyclic standards. So cycles are already in the bloodstream of measurement. Now part 41 shows when cycles are fundamental, topology becomes unavoidable. If you want a foundation that can produce repeatable standards, then somewhere you need closure. And closure is topology. If you avoid closure entirely, you risk that every attempt to return drifts into untestable, infinitely detailed difference. You may still have a private universe, but you lose a clean path to public invariance. This is why we call it topological inevitability under our firewall constraints. Not a claim that every aspect of everything is literally a circle, but that the minimal closure structure is forced when you require the kind of repeatability that science needs. Now we install the firewall properly, with prediction and falsification. Quantization will always trace back to closure invariants, winding numbers, holonomies, or equivalent topological structures. In plain language, whenever the world produces whole numbers only, there is a hidden return to start condition in the architecture. This means that if future physics discovers new quantized phenomena, the model predicts that deeper analysis will reveal some closed-loop constraint, maybe in an abstract space, maybe in an emergent geometry, maybe in gauge structure, but it will be there. Derive fundamental quantization without any closure topological invariant structure. This is the clean challenge. Show me a case where nature produces discrete, integer-like quantization in a way that does not secretly depend on any form of closure. No loops, no holonomy, no boundary matching, no single valuedness constraint, no topological invariant hiding under a change of language. If such a derivation exists and is truly free of closure, then part 41 fails. Notice how strict this is. It's not enough to say, I can write down integers. You must show that the integers do not arise from a global consistency requirement, because global consistency is exactly what topology formalizes. So we attempt to falsify ourselves by scanning what we know. Bohr, loop. Schrödinger, phase closure. Particle in a box, boundary closure. Aharonov-Bohm, loop integral. Berry phase, cyclic parameter loop. Geometric quantization, integrals over closed surfaces being integer multiples. Dirac quantization, charge with monopoles, single-valued phase around the loop. Spin quantization, rotation group closure properties, and phase behavior under loops in orientation space. Everywhere we look, closure returns. This doesn't prove it for all possible worlds, but it does show the pattern is deep and resilient. And, importantly, it shows the principle is not vague. It is testable. Produce quantization without closure, and you've cut the spine. Now, let's translate the technical word holonomy, because it's one of those words that can scare people away, but is actually simple. Holonomy means what you pick up when you go around and come back. If you walk around a mountain and return, you may end up facing a different direction than you started because the path twisted you. That difference after return is a holonomy. In physics, the thing you pick up is often a phase, and phases on a circle are counted in turns, integers. So even the more advanced language still points to the same skeleton. Go around, come back, see what changed. The allowed changes are counted. Now we return to the minimality question again, because parsimony is still watching us. Why not a line segment? A line segment is finite, but it has boundaries, two ends. Ends create special places. Special places invite smuggling. New boundary rules, edge conditions, asymmetries. With a circle, there are no privileged endpoints. Every point is like every other point. It's the cleanest compactness. Why not higher spheres? Higher spheres are also compact and boundaryless, but they add dimensional complexity. In a parsimony regime, you do not add degrees you cannot operationally justify. The circle gives you closure with minimal dimension. Why not a torus? A torus has multiple cycles. Multiple cycles means multiple independent integer invariants. That might be true for some later structures, but at the foundation, we are still sealing the silent ground. One cycle is enough to create closure and integer winding. Adding more cycles is additional structure we haven't earned. So S1 wins not because it's fashionable, but because it's the minimal, non-trivial closure compatible with our earlier seals. And now the most important sentence of the whole part becomes clear. If phi becomes representable at all, it will be representable first in the smallest closure language available. And the smallest closure language is S1. Now let's make one more leap, because this is the aha that makes listeners feel it in their bones. In part 40, we said, units come later through cyclic standards. A second is defined by counting cycles. A meter is defined by light travel per accounted fraction of a cycle-based second. Even mass is now tied to Planck's constant via apparatus that relies on electrical and quantum standards, again deeply linked to repeatable cycles. So cycles are not a side feature. They are how measurement breathes. Now part 41 says, cycles are topology, and topology yields integers. So the universe speaking in whole numbers is not a surprise. It is the inevitable consequence of building public reality out of repeatable comparators. When you make science possible, you make integers possible. And once you make integers possible, they show up everywhere in quantized energy levels, in winding numbers, in charge quantization, in topological invariance of materials, in discrete stability classes of defects, in holonomy around loops. This is why we can say with firewalled confidence, quantization is not an added rule, it is the shadow of closure. And closure is not an added decoration, it is the minimum structure that allows exact return. An exact return is what repeatability requires. Now we also keep the Part 38 discipline alive, extensionality. If someone claims, my theory explains quantization without topology, we apply the same razor. What observable difference does your non-topological explanation produce? If none, then you have only renamed topology. If it does produce a difference, then show the experiment. This prevents storytelling disguised as explanation. Now we're ready to state the listener carry in the cleanest way. Closure forces whole numbers. That's the carry. Not quantum mechanics is weird. Not the universe is made of discrete atoms because it feels right. Not nature likes integers. But if something must return exactly to itself, then only whole can survive. A wave on a loop must fit an integer number of wavelengths. A phase going around must return with 2 pi n. A global invariant measures how many times you wrapped, and the wrapper count cannot be 3.7. It's 3 or 4. This is the quiet power of topology. It turns continuous motion into discrete classes. And now, because you always want where we came from and where we're going, here is the bridge in one breath. We came from no units, no scales, part 40. The foundation carries no rulers, so any structure we accept must be scale-free. S1 is scale-free. It is closure without a built-in meter stick. And S1 produces integers without units, winding counts. So now we have a mechanism for discreteness that obeys parsimony and avoids smuggling. Where we're going next, part 42, is even more severe. The pure capacity seal. Undifferentiated phi has no internal knobs, no parameters, no built-in constants. That means even the settings of reality cannot be smuggled into the ground. They must emerge later or be reinterpreted as relational invariants. Part 41 is the bridge. It shows how, even without units and without knobs, the foundation can still force discrete structure, because topology doesn't need a ruler and doesn't need a dial. It needs only closure. You're walking. You don't know what world you're in. Locally, it all looks like a line. But you keep going, and one day you return to where you started. At that moment, the universe hands you a gift, a number you can trust. Not a meter, not a second, not a joule. A simple count of how many times you wrapped. And that count is an integer. The loop closes. The return is exact. And whole numbers appear, not as a human invention, but as the inevitable grammar of closure. Closure forces whole numbers. When phi becomes representable, the minimal non-trivial compact closure is S1. And the moment a loop exists, nature gains invariants you can count, winding numbers, holonomies, integer classes. Quantization is not magic added on top of continuity. It is the inevitable consequence of exact return. If future physics finds new discreteness, we predict it will trace back to a closure invariant. To falsify this, derive fundamental quantization with no hidden closure anywhere. Until then, treat integers in nature as footprints of loops, sometimes in space, sometimes in phase, sometimes in the abstract geometry of possibilities. Peace be upon you.